So I want to tell you something today about how we used or started to use auto-differentiation within the ACTS toolkit. So this will be now very much focused on application, and so in contrast to the previous talks, there won't be any details on auto-differentiation implementation or things like that. So as I already mentioned in the beginning, I'm a PhD student in the University of Regensburg, and I'm doing my PhD in collaboration with the ACTS team and working on machine learning based algorithms for tracking. But and this auto differentiation thing has somehow developed as a side project of this, which was also inspired by Lukas Heinrich, which some of you might know. Yes. And what I will show you today is first I will introduce the Autodiv library, which I used to implement all the things with Autodiv. Then I will give a short overview of what ACTS is. And then I will highlight two use cases of Autodiv which we currently have or planning to have in ACTS. Okay, so Autodiv is a C++17 library, which you can find on GitHub. It's like most software today, and it supports forward differentiation and reverse mode differentiation, whereas the forward mode differentiation is implemented with expression templates, so it's relatively fast, I would say, and the reverse mode is implemented using a state unique pointer in a graph of these objects, so that's relatively slow, I would say. But we will use, I used forward mode in all my examples because we have the use case of us has relatively balanced Jacobians, so we get much better speed with forward mode Jacobians. So I will show quickly here some how the API of Autodiv looks. So I think it's a very well designed API which uses these new C++17 features. So we have as Autodiv provides here, for example, for the forward mode, this type Autodiv dual, which then allows the program to trace the control flow and to compute the derivatives. And there we have these API functions like derivative or Jacobian, where you can just pass any function object or lambda or anything which is callable with a call operator. And then you pass your dependent variable in this nice with respect to function, and you pass your the point where you want to evaluate the derivative, and yeah, then you're done effectively. And I think that's a really nice interface and easy to use. So it's a header-only library, which is also very beneficial and uses this operator overload mechanism we already heard of somewhere. And yeah, and it supports eigen, so that's also very nice because ACTS is built upon the eigen linear algebra framework. Yes, I did some small performance benchmarks with Autodiv to justify if it's a okay choice. And the first thing we see that the reverse mode is really, really bad compared to almost everything else I've seen. So the reason is there, I think that for almost every operation, they do a dynamic memory allocation. And that's, I think, really not a good design. But for the forward mode, we have really good performance, at least compared to these other frameworks I compared it to. So for our use case, Autodiv was really a good choice, I think. Then I will quickly introduce ACTS. ACTS is a tracking framework also written in C++17. and it combines a bunch of algorithms used for track reconstruction, like track finding, track fitting, vertexing algorithms, and things like that. And there are provided production quality implementations of these algorithms. So parts of ACTS are also used in the Atlas software stack. And as a second purpose, ACTS also serves as a R&D platform at the moment, mostly for parallelization and machine learning. And you also can find it on GitHub, and it's also very actively developed. So where do we want to use Autodiv in ACTS? So as a first step, we implemented Autodiv as a plugin and use it for the validation of several places or algorithms in the code where derivatives occur. And as far as we know, but I'm not sure if that's actually true, this is one of the first uses of Autodiv in high energy physics C++ reconstruction code. But I'm not sure if this is actually true. We also just don't know any other use case. So for the implementation, we really focus here also on the interface. So it's not, because we at the moment only use it for validation purposes, it's not focused on the optimal performance here. And as I mentioned also in the overview at the beginning, we have two applications at the moment, which is the covariance transport in the propagation and the alignment derivatives. And I will now quickly explain these two use cases and how we implemented it with Autodiv. So to give an overview over the covariance transport, there the key problem is that we want to propagate a track from one surface to another one. And we do not only want to propagate the track parameters, but also the covariance matrix. And therefore, we need a Jacobian between these two surfaces. And this Jacobian also must be built up iteratively during the integration. And in here you see it in the orange shaded formula. Here we want to apply Autodiv. So and depending on the parameterization of the track, we have here matrices involved from the range of 6x6 to 8x8 matrices. So yeah. And this is how is this implemented? So one benefit of ACTS is that we have there a highly modular and templated structure. So we have the propagator as a high-level class, which is then equipped with a stepper. And this stepper also can be modified by templating it on several extensions. And these extensions encapsulate the physics, which is actually needed for the integration. And so what we have to do here is simply to template, in principle, this extension and use Autodiv dual instead of double. And then we can just compute our Jacobians from this function. Yeah, how is this then actually implemented? Here we chose to create kind of wrapper extensions for this, which we can equip with a basic extension as a template parameter. So a template parameter which itself is a template again. And then this wrapper extension internally holds two instantiation of this, one with double, one with Autodiv dual. So and the double one provides the public interface, which is then identical to the basic extension, the underlying extension, where the Autodiv extension can internally compute the Jacobians with Autodiv. Yeah, and so because the public interface is identical to the underlying extension, we can just plug in this wrapper extension into the default, into the software or into the source code. And with no modifications anywhere in the code, we can just run it. And it can also be used for any kind of extensions. At the moment, there are two extensions, but if for some reason there someone who wants to have a different extension, he can just use the wrapper extension and generate the covariance transport with this automatically, which is, I think, quite a nice interface. I have also done, even though this is a validation purpose, I have done some small performance evaluation, and we see that the numerical validation is, which is not so surprising, I think, is much slower than the automatic differentiation and the hand-coded differentiation. But we also see that Autodiv is not as fast as the hand-coded differentiation, and I think this has several reasons. And one is also that the hand-coded derivatives can take some shortcuts with which the Autodiv one cannot do, because it computes all occurring derivatives. Yes. Then as a second use case, we have the alignment derivatives, which is still a work in progress project. Yeah, just for the overview, the alignment parameters determine the position and the orientation of, for example, a surface in the coordinate space. So they consist of 3 space points and 3 angles. For a reason which I not really can explain here, we need this derivative of the bound track parameters, so the parameters which are defined with respect to a surface, and these alignment parameters. And yeah, this we also want to compute with Autodiv, and this is not yet how the interface can look for this. This is just a kind of implementation sketch. And the difference to the thing before is that we have here a kind of users applied part of the derivative, because in context of this part of the software, we don't have access to the equation of motion in the magnetic field. So one part of this derivative is user supplied in this case, and but the other parts we can compute with Autodiv, again in a similar manner as before, and then we can combine all these things and have our final derivative. Yes, that were these 2 use cases. And yeah, to wrap this up, it's because we have these nice header-only libraries, it was very easy to include this in a big project such as ACTS, and we can use it as a very easy tool to validate these derivatives in all kinds of situations. But as I already mentioned, for performance reasons, this cannot really replace the hand-coded derivatives yet, question mark. So maybe there will be techniques in the future, and we also already saw some interesting things there in the talks before. So that maybe someday we can use it really in these places, not just for validation purposes. Yes, that was it from my side. So if you have any questions, feel free to ask.
Thank you. Questions? Okay. So,
sorry, was that a question, or can I ask? I didn't want to interrupt.
Yeah, go ahead. Sorry.
Actually, I wanted to understand, and maybe this isn't so much a question for you, Ben, but what would it take to get to the point where some of these other tools perhaps could be brought to bear and be, I don't know, perhaps not as efficient, but close enough that they are easier to use than to actually have to hand code the derivatives. And I don't know who that's a question to, but I guess I'm asking about next steps.
Yeah. From what I've seen, I've just before this meeting, I looked through the C++ proposal for the C++ standard, and I think that really would, if that would happen somehow, that really could be a game changer for this, I think. But yeah, for the other things, I'm not sure if I have a good answer for this. Yeah, it's just my feeling is that such a framework like ACTS don't maybe want to depend on compiler plugins, but I'm not sure if that's in fact true. Yeah, it's just what I feel. So maybe someone else can give a more educated answer.
Yeah, I can take a stab at it. So the advantage that we think there is when having something implemented close to the compiler is the fact that nobody else knows better your C++ code than your compiler. And as you said, the generic expression templates or the generic autodiff derivatives that are generated with are not as efficient as the one that you would code by hand because you can take shortcuts. So can the compiler. And that's why I personally think that having something that's close to the compiler can be allowed to take more shortcuts than the generic implementation of automatic differentiation that's in a library. How does that happen?
Oh, sorry.
How that would happen, I don't know. For example, if we hope for the C++ standards to have like automatic differentiation, that can be a career-long effort. C++ does not really like big proposals to be shipped quickly. So a proposal of that scale, if stars are aligned, it would take probably at least 6 years or so to happen in the standard. And then back to acts, it would be, I don't know, probably 9 years because we want to have like one cycle of standards before the actual one so that we can catch up with new features and still have good compiler coverage of the features that are in the standard itself. I don't know if that makes sense.
Let me follow up with that just with a quick question. If you look at the shortcuts that Ben has to do in order to make it efficient, like move it from just validation into something more mainstream, would the compiler be able to do those shortcuts? Would the modules, the shortcuts, the compiler's view tends to be reasonably local. It does one unit at a time, I suppose. Is its view large enough to implement those shortcuts? I mean, would that approach work?
I mean, I can give an example of something somewhat similar that we're able to take advantage of, say, in enzyme, which is, you talk about like module local and or potentially even like function local, and indeed many of the existing compiler analyses and optimizations tend to be say function local scope. But one big part of say the question as to whether or not you can cache something or you can just reload it in the future is alias analysis. So whether or not it's modified, and having even like minimal markings that exist, say like restrict or even like read none on some of these things, permits some of this cross-module and cross-function optimization that is something that you wouldn't really be able to get even working at the higher level with these sort of pieces without inherently making a lot of assumptions. But you can sort of auto-deduce because there's a lot of infrastructure in place for being able to do even some of these like relatively weak analyses like alias analysis in this sense, that have a massive performance benefit for automatic differentiation.
Okay, that's very cool and very good to hear. Thank you.
Maybe a follow-up on what Billy said. So another way that I see it is, for example, when you do automatic differentiation in your generic purpose programming language, you essentially turn into a subdomain, which is the mathematical subdomain. And there are some generic compiler assumptions may not be valid, but they can be valid for the subdomain of mathematics. For example, you know your tensor operations. You know that sometimes when you multiply by 1 or divide by 1, you know the result. So I would think that if for example, we have a system that's configurable to some extent, to be able to express that domain specific knowledge, say, I don't know, in the case of CLAD, there are kind of replacements. So you can say, well, if you differentiate this function, don't go bother, just use this, or this is this shortcut. So if we can do it in a more structured and more easy to express way, I think what you do by hand, since it's, as long as it's algorithmic, it's not like something that you will just struck and you figured it out and then you reinvented the new thing. Every algorithmic substitution that you do in your custom derivative, in your handmade derivative, can be replaced by a compiler who's sufficiently smart, of course.
I think that's a fantastic idea. You'd like to be in a position where people don't feel like they have to resort to that, except in the very end game where they're just trying to squeeze every last bit of a performance. Right? It would be nice if the static analysis tools and other things could tell the compiler, I suppose, enough that Autodiff could be constructed relatively efficiently, except for some corner cases, and those corner cases you could then implement the fallback. And I think with that, it would gain adoption relatively quickly, because it would be seen as not having to do all that much work.
I think that's one of the benefits, that if we somehow properly merge CLAD and enzyme, we would have that thing, because we will have some exposure from the front end, and then we will somehow send it to the back end, so that the back end also can do something that's specific given the surrounding context. So this has been, yes, indeed a topic of something that I have been thinking about, and of course with Billy's input and his knowledge. But I think, yeah, we need to see. Definitely something worth exploring. I don't know how it would go.
Yeah, sort of generalizing that slightly. The other example I'll give of this is sort of like another integration, except more in the Swift domain. And the reason why I say that specifically is Swift happens to have built into the language itself automatic differentiation, and as a consequence, for like most of their functions defined in their standard library and the likes, they have like the derivative of sort, for instance, is to do like a select and like reduce this stuff up and down, and so on for a lot of these routines. And this obviously is beneficial to have that information for the sake of, if there's a high level derivative of something that may, for similar reasons the previous discussion, may be more efficient from some like high level semantic information, then you should try to integrate that. Swift, however, suffers from the fact that because they do all of these like rewrite replace tools, from the same reason where they have to apply prior to optimization and the like, mean that in practice it's quite slow. So analogously, tools that do this sort of like combination of like high level, low level interfaces, I think is, again, the way forward for this, in which you're able to say, take information about those like existing front end level or even otherwise level semantics that you're trying to differentiate, and then combine them with all of the other pieces in the stack of like the AD tool. You'll get something that effectively combines the best of both worlds. So you'll be able to say differentiate with the high level knowledge that you can get rid of this entirely because, you know, activity analysis said so or whatever. And with the fact that you have all of the very efficient scalar, which is quite important for like most of these codes in practice, but you can still get rid of like the big swaths of, you don't even need this entire function call. And that's kind of what I think a lot of these things are aiming towards. And that's, for instance, why like in this enzyme, we have like the explicit foreign function interface, and we hope to integrate that with like, you know, front ends that can provide this tool with potentially like more high level AD information, e.g. like the CLAD for like C++. We can imagine like the Swift like front end itself, and similar for the Julia. So I think, again, really moving forward, similar to how you have like all these existing compiler pipelines just for regularly optimizing code, none of which is optimal. So you have your DSL that has some specific pieces of information for being able to, you know, make your tensor codes and like get rid of your entire tensor ops. We need the equivalent of that pipeline for AD.
Speaking of Swift, I think we have a person here who contributed to Swift and can tell us what is the big benefit of having it as a first-class citizen. I'm not going to mention the name.
Hi. Yeah, I worked a bit on Swift. Sorry, what is the question again?
So the question
what is the benefit
is
of like having ID as first-class citizen?
Yeah, what is the benefit when you have everything under control, when you have the front end aware of being able to automatically differentiate, and also the backend under control? So what is the benefit from having those two elements in a single language?
Well, I think in principle it is not so different compared to having ID coming from a compiler plugin, let's say, in the same way as we have it in CLAD. It's just, you know, on one hand, you can imagine that having it as a first order feature in the language just makes it kind of more well-known or more popular, so that people are aware that this is the way to do stuff. And of course, it also guarantees that there is sufficient support for every feature in the language, so that you are not restricted to some subset of language, and you can use it pretty much with everything under reasonable assumptions. And of course, well, the way Swift does it is kind of intermediate. So on one hand, they have some implementation of the front end. For example, some derivatives for mathematical functions are defined again as other functions in Swift. But on the other hand, the actual automatic differentiation happens in Swift intermediate language, which is in some sense an LLVM IR, but more of a high level IR compared to LLVM. So it is something I would say in between of Clang AST, abstract syntax tree, and LLVM IR, which is, I would say, kind of close to the assembler. And from this, they also have some benefit in the sense that it is simply easier to work with it. So as we mentioned, it is very tedious to handle, for example, C++ abstract syntax tree for differentiation in general case. And maybe, for example, as Billy presented, it is optimal in some cases to do differentiation in the IR. But also on the IR, you don't have really a lot of information from the language itself. So maybe it actually makes sense, for example, to have some wrapper in the language directly that kind of wraps your IR-based ID implementation, so that, for example, you have a nicer API for the user and so on. And yeah, it's basically a combination of everything. I would say it's not like a single thing. It has, in the end, it has kind of nice API, also good documentation and kind of good visibility for the user, but also it has a reasonably efficient implementation on the low level. And it also has a good extensibility in the language, in the sense that you can define specifically what type is differentiable and in what way you want to differentiate it. For example, what is a 0 for your type, what is 1 for your type, what is the plus operator for your type, and so on.
Yeah, and also I think they had their intermediate representation being able to capture high-level concepts like mathematical operations. So I think in Swift, correct me if I'm wrong, but I think in Swift, they can detect where the tensor operations are and they can do stuff symbolically, for example.
Yeah, sure. And also they can do more customized things. So for example, if they know that they are dealing with sparse tensors, they can specifically define a type for the derivative of this tensor that would not be the tensor itself, but it would be something like a sparse tensor. So for example, in class, the way we are handling it, if we have some type, for example, okay, double, then its derivative is going to be double again. And in general, for any type T, we assume that its derivative also should be represented by type T. But you can also optimize that if you know that your derivatives have some special structure, for example, that they are sparse. And you can, in Swift, you can specify that for example, for tensor, you want to have a derivative of different types that is not a tensor by implementation, but mathematically, it still implements all the methods that are required for tensor, for example, additions and so on.
Okay, thanks for the discussion. It was very useful to me and very educating. Thanks